Hi, my name is Nick Theobald. This is my presentation on the prototype of a speech recognition device for hearing impaired dogs. On the left here, we have the finalized prototype for the speech recognition device and the manual controls that could be worn by the owner or placed in a stationary position of the room. And on the right, we have the final vibration collar that could be inserted into a collar or mounted on a harness. So just to start with a basic overview of hearing impairment in dogs. The first type is age-based hearing loss, also known as presbyculosis, which typically occurs around 8 to 10 years of age. And this can actually have a great effect on the declining cognition of the senior dog, as well as the quality of life. Unfortunately, there's a rather minimal amount of research on this topic. Then there's congenital hearing loss, which is the type of hearing loss that occurs at the birth of the dog. And this is estimated to affect up to 30% of Dalmatians, 14% of English setters, 10% of Border Collies, and a rather high percent of other dog breeds. The effects of hearing loss are, of course, reduced quality of life. It results in difficulty training and bad behavior, of which vibrating collars can actually aid in communication with the animal to correct some of these issues. And these can actually be minimized with the use of hearing aids and cochlear implants. However, these are expensive and not effective for all dogs. So for communication aids for people and dogs, for people, of course, we have hearing aids, which are rather effective but expensive. Real-time captioning devices, which are devices that transcribe real-time audio into readable text. These are relatively widely available, are effective, and can work online and offline. Then there's alerting devices, which are devices that alert the user of certain events, such as smoke alarms, ringing phones, doorbells, etc. These are widely available, rather effective, and also available online and offline. However, for dogs, really there are only hearing aids, which are not always effective and are expensive. And then there's vibrating collars, which are very effective, but does, as far as I can tell, always requires the input from the owner. So for my project, I am proposing the voice-activated vibrating collar, basically. The purpose of this is to aid and enable communication with hearing impaired dogs and activate automatically and minimize the need for manual controls. The objectives for this design are for it to be lightweight, be power efficient so that it can run at least 24 hours continuously, and of course be safe, meaning that it should minimize the number of false recognitions and, of course, if the design got far enough, have safe battery technology so that it doesn't cause any fires or injure the animal. The constraints for this design are it needs to be limited to general purpose hardware such as the ESP32, Raspberry Pi, or just a Samsung S10 Plus. It needs to have no reliance on the cloud once it is running, and it is highly preferred just to have one device, although 2 devices is also acceptable if necessary. The functions for this device needs to be that it can recognize a set of vocal commands, provide tactile feedback to the dog, and enable manual controls wirelessly. And as far as I can tell, there aren't any other voice-activated vibrating collars, so really what I'm taking inspiration from are speech-activated robots, the wake word recognition in voice assistants and smartphones, and other offline voice-activated devices. So for the design options, the first option is a single self-contained device inside the collar or harness where the device takes care of all of the voice recognition, Bluetooth connectivity, and driving the vibration motor. This can be handled by a single power-efficient device that can handle speech recognition and Bluetooth. This could be the ESP32 or Raspberry Pi 0W. This is the preferred design just for usability so that everything's contained in one package. However, this has the highest anticipated difficulty and the lowest anticipated runtime just since everything's having to run out of such a small package and battery capacity. So for the second option, we have 2 separate devices. a device similar to the first option that just handles the vibration motor and Bluetooth connectivity, and a secondary device that handles the voice recognition and Bluetooth connectivity. So the first device could be handled just by ESP32 or other Bluetooth-enabled microcontroller, and the secondary device could be handled by another ESP32, Raspberry Pi 0W or 3B+, or the Samsung S10 Plus. This also opens up the options for different microphones. For example, you could use Bluetooth earbuds or headphones through the hands-free protocol, or another ESP32 with I2S microphone and A2DP Bluetooth protocol. So for possible methods for speech recognition, the first two options here are really the ones I really considered. We have TensorFlow Lite and PicoVoice Porcupine. And then we have three other potential options: the Espressive WakeNet, a non-machine learning option, which compares the output of bandpass filters, and then, of course, sort of dedicated hardware that is available all over the internet. The first option is the highly desired option, since this would allow everything to be contained in one package. TensorFlow Lite, which has an option for speech recognition and wake word recognition. We have training code that is readily available in Google Colab, and it has the possibility to be trained on non-verbal audio, such as smoke alarms, doorbells, things like that. This is available for the ESP32, Android, and Raspbian. Then we have PicoVoice Porcupine, which is just a wake word detector. This is a free and paid service with easy model training through their website. This is available through Android, Raspbian, and certain microcontrollers. And then, of course, we have Espressive, which is just another wake word detector. The model training is unknown, and it's really only available for certain ESP32s. Then we have the other two options, which aren't really considered in this design. So for the design process, I first needed to determine whether one or two devices were most feasible. So I first started looking at some of the more central design aspects for both options, which is ESP32 Bluetooth connectivity, Android Bluetooth connectivity, Raspberry Pi Bluetooth, and ESP32 TensorFlow Lite. So the ESP32 and Raspberry Pi Bluetooth were relatively easy to work out. The documentation was decent and turned out okay. The Android Bluetooth connectivity was rather difficult and in the end didn't end up working out. So from this, Android was really eliminated as a hardware option. As for TensorFlow Lite on the ESP32, from the beginning I had a lot of issues with the original board I had purchased, so I sort of moved on from this design option while a new board was ordered so that I could still have Bluetooth. But really, the single device option was eliminated due to early issues with the ESP32. So then I moved on to the two design option. First looking at PicoVoice for Android, which didn't really work out since Bluetooth didn't work out for Android. Then PicoVoice for Raspberry Pi, which ended up working out pretty well. And then I looked at different motor controllers and different microphone options. So really from this point, I moved forward just with the two device option. Moving on to the current design that I have, really the caller is just controlled by an ESP32, which has Bluetooth and Wi-Fi capabilities. It has a buzzer and LED for indicating the device's status, and then a motor driver and the vibration motor. And then the speech recognition and manual controls module, which has a Raspberry Pi 0W, a button for manual controls, an indication LED, and then the I2S microphone. So for the operation of both of these, you just apply power through a USB device for the moment. 5 volts and 3 volts could be applied to both of them, but I didn't get far enough into the design to really consider that kind of thing. So you apply power, on the collar, the LED, motor, and buzzer briefly flash, pulse, or beep to indicate that the device is powering up. The speech module LED flashes. Then you can log into SSH, start the script using NoHup, and then close SSH, and from this point forward, Wi-Fi is no longer needed. So both modules will connect, and both LEDs should turn solid once they are connected with Bluetooth. So then moving on to the different commands, we have 3 different spoken commands. We have hey mojo, mojo come, mojo sit, resulting in 1, 2, and 3 quick pulses from the vibration motor. Then we have the manual button commands, 1, 2, and 3 presses, which results in 1 quick pulse from the vibration motor and 1 LED flash, and so on. Then we have a location mode, where you can press the manual button 4 times and the buzzer on the collar will sound. And then we have 5 presses on the button will basically power off the Raspberry Pi. This won't power off the collar since it's not nearly as critical to power that off, since it won't result in corrupting the operating system. Then moving on to the testing results. First, I looked at the power draw requirements for both modules. For the collar and the controller, they both had, for the collar, it had an idle power draw of about 90 milliamps, and the controller had about 203 milliamps. If you spoke one word in about 18 seconds, you got about 120 milliamps from the collar and 201 milliamps from the controller. And then if we extrapolate this out to 10 minutes, you get about 90.9 milliamps on the collar and 203 milliamps on the controller. On the right, we have the current draw for both of the devices. As you can see, the Raspberry Pi actually requires less current when the recording and Pico voice shut off and the Bluetooth sends the message. But for the ESP32, you can see that the current rises quite a bit as it turns on the vibration motor. And at the bottom here, we have the accuracy tests given different audio conditions. So we first have baseline, where there's no background audio. We have another where we have a thunder sample playing in the background, a vacuum sample, and then just random talking. All of these are just examples on YouTube that I will link at the end. So on the horizontal axis, we have the actual command, and on the vertical, we have the predicted command. The first number before the comma is the number of times that command is actually recognized, and the second number is the number of times that the command was recognized as a secondary recognition. So it recognized it as 2 subsequent commands or 3 commands. I don't really know why this is possible. It shouldn't be, so I'm not entirely sure what's causing this. But as you can see, for the first 3 cases, it accurately recognizes the true command all the time. However, there are a few secondary commands that it recognizes occasionally. But once we get to the third test with the talking audio, we can see that it actually starts to have completely missed commands where it doesn't recognize any of the commands, and also where it recognizes other commands as being the true command, where the true command isn't recognized at all. So in conclusion, I think that my design achieves all of the objectives relatively well. It is relatively lightweight. It is power efficient, and in 24 hours, the collar would require about 2,000 milliamps, and the controller would require about 4,800 milliamps. It is relatively safe. There are no false triggers during idle, and there are only some false triggers during the verbal tests. It adequately achieves the needed functions, and I've recognized a few improvements in future works, mainly focused around better form factor and power usage. So a designed and assembled PCB would be highly beneficial, as well as a dedicated battery and battery management system, and of course a better sleep modes, better controls from an app, a better Bluetooth protocol, and finally probably replacing the ESP32 with a lower power microcontroller. Thanks.